Between 1945 and 1970, the United States built more roads, dams, and highways than any nation in the history of the world. The interstate highway system alone moved 3.5 billion cubic yards of earth. And the machine that moved most of it was the cable-operated bulldozer. At construction sites across America in the 1950s, Caterpillar D7 bulldozers worked 12-hour shifts, 6 days a week. Their operators sat on open platforms with no seatbelts, no cabs, and no rollover protection. Beneath the blade, 3/4-inch steel cables carried 12,000 pounds of tension. Those cables controlled everything: blade up, blade down, blade angle. And when one of those cables failed, it whipped through the operator's position at over 100 miles per hour. The fatality rate for construction workers in the 1950s was 75 to 100 deaths per 100,000 workers. Today, that number is 9.6. But the men who operated these machines never made the evening news. They had no union, no advocacy group, and nobody keeping count. This is the story of how cable-operated bulldozers built modern America, and what it cost. To understand why these machines were so dangerous, you have to understand how they actually worked. A cable-operated bulldozer, like the Caterpillar D7, used a system of wire rope, drums, and pulleys to control the blade. The operator pulled steel levers connected to clutches, which engaged rotating drums wrapped in cable. Pulling one lever raised the blade. Releasing it lowered the blade under gravity. A separate cable controlled the blade angle, allowing the operator to tilt the cutting edge left or right. The problem was the cable itself. A standard 3/4-inch wire rope on a 1950s bulldozer carried a working load of around 12,000 pounds. These cables ran through 8 to 12 pulleys, each one a potential failure point. When a cable under that much tension broke, the stored energy released instantly. Engineers later calculated the whip speed of a failed cable at between 100 to 150 miles per hour. At that velocity, braided steel can sever bone. The control levers themselves required 15 to 40 pounds of sustained pressure. Operators pulled those levers for 8 to 10 hours straight, day after day. There were no power-assisted controls, no ergonomic handles, just steel rods connected to steel clutches, and the operator's grip was the only thing between controlled movement and catastrophic failure. Every single safety feature that modern operators take for granted did not exist. There was no rollover protective structure, ROPS. There were no seatbelts, no enclosed cab, no backup alarm, no safety sensors, and no kill switches accessible from the ground. The operator sat in the open air on a steel seat, surrounded by spinning cables, exposed pulleys, and a diesel engine producing noise levels that would be illegal on any modern job site. In Pennsylvania in 1954, a Caterpillar D7 was working a highway grading operation, pushing earth along a muddy cut where the roadbed was being shaped for what would become part of the Pennsylvania Turnpike extension. The heavy steel blade was raised when the lift cable failed. The broken cable whipped through the open operator station like a steel whip and struck the operator in the chest. He was killed instantly, slumped over the control levers on the seat of a machine still idling in the middle of a half-finished road. The man was 34 years old, married, with 2 children. When investigators examined the frayed cable afterward, they found it was 60% compromised. Individual wire strands had been snapping for weeks, possibly months. The cable had not been inspected in 3 months. The contractor who employed the operator faced no penalty of any kind. There was no federal agency to report to, no investigation protocol, and no legal requirement that the incident be documented at all. This was not an unusual case. Cable inspection was entirely the operator's responsibility. There was no regulation requiring it, no company policy enforcing it. And the economics worked against it. A full inspection of all 8 to 12 pulleys on a cable system took over 4 hours. 4 hours of downtime meant 4 hours of lost wages for the operator, and 4 hours of lost production for the contractor. An industry study from the late 1950s found that 73% of operators admitted to only greasing and inspecting the pulleys they could easily reach, skipping the ones that required crawling under the machine or removing guards. They called it Pulley Roulette. With full maintenance, a cable system lasted roughly 2,000 to 200 operating hours before replacement. With partial maintenance, that number dropped to 800 hours. Operators were gambling with their lives to avoid losing a day's wages of $20 to $40. If you're watching this and finding it useful, take a second to hit subscribe. I cover construction disasters, heavy equipment history, and industrial safety every week. But the cables did not have to be worn to be deadly. This is something almost nobody knows. Below -20 degrees Fahrenheit. The steel used in the 1950s wire rope underwent a transformation. The metal became brittle, losing its flexibility. Engineers call it a ductile to brittle transition, but operators in Alaska and northern Canada had their own name. They called it glass cable. In Alaska, in 1959, a bulldozer was pushing frozen ground along a pipeline access road in the middle of winter. The temperature had dropped to -35 degrees. Snow covered the tracks and the undercarriage of the machine. The blade lift cable was only 3 months old. It had passed inspection. There was no visible wear, no broken strands, nothing to suggest failure. Then, without any warning at all, the cable snapped clean in the frozen air. The stored energy whipped the heavy steel blade 90 degrees. The operator's spine was broken by the impact. He survived, but never walked again. The cable, when examined later, showed a brittle fracture surface that looked almost like broken glass. There had been no gradual failure, no warning signs of any kind. The cold had turned flexible steel into something that shattered. This was a known phenomenon. Cold weather cable failures were documented throughout the 1950s in northern states and Canada. But the information never reached most operators. There was no centralized safety communication system, no mandatory reporting requirement, and no mechanism for an operator in Montana to learn from a failure that happened in Alaska. Cold was not the only invisible threat. There was another failure mode that killed people who were not even operating the machine. In Kentucky in 1958, a surveyor was standing on a dirt construction site next to an idle Caterpillar bulldozer. The diesel engine was off. The machine had been sitting motionless with its heavy blade raised for 45 minutes. The surveyor was taking grade measurements with his equipment, standing about 8 feet from the front of the blade. Without any warning, the blade dropped straight to the ground. The lift cable had failed, while the machine sat idle on the construction site. The surveyor was killed instantly. The autopsy and subsequent investigation revealed that 80% of the cable's individual wire strands had already been broken at the point of failure. The remaining 20% had been holding the entire load of the raised blade through friction alone. For 45 minutes, friction was enough. Then it was not. Operators called this the phantom blade drop. A cable could be 60, 70, even 80% compromised and still hold. It might hold for 10 minutes. It might hold for 2 hours. There was no way to predict when the remaining strands would let go. And because the blade was gravity-operated on a cable system, the only thing preventing it from crashing down was that cable. Texas, 1956. A different kind of cable failure on a dusty construction site in the summer heat. The angling cable, the one that controlled the left-right tilt of the heavy steel blade, failed during an earth-moving operation. When the cable broke, the blade swung sideways like a 2,000-pound pendulum on the front of the machine. A foreman standing 12 feet away on the open dirt was struck and killed instantly. The operator, sitting on the steel seat directly above the blade, was completely uninjured. He did not even know what had happened until he looked back and saw the foreman lying on the ground behind the bulldozer. Montana, 1957. An operator suffered a heart attack while driving a cable bulldozer across an open construction site near a large water reservoir. When his hands released the steel control levers, the levers returned to neutral position, which stopped the blade movement. But the heavy machine kept driving forward in whatever gear it had been in, crawling across the bare earth toward the water. The bulldozer drove straight into the reservoir and sank beneath the surface. The operator's body was recovered 3 days later, still strapped to the open steel seat, underwater. There was no kill switch, no dead man's control, and no way for the machine to stop itself when the operator could no longer operate it. These were the machines that built the interstate highway system. These were the working conditions that the men who built modern America accepted as normal. And the reason you probably never heard about any of this is simple. There was nobody whose job it was to tell you. If you want to understand how dangerous heavy equipment really was before modern safety standards, make sure you subscribe. This is the kind of history that does not show up in textbooks. But here is something that challenges the entire narrative of cable machines being the dangerous ones, and hydraulic machines being the safe alternative. Between 1950 and 1954, the first wave of hydraulic bulldozers entered the market. They were marketed as safer, more precise, and easier to operate. The cables were gone, replaced by hydraulic cylinders, pumps, and fluid under pressure. And for the first 4 years, hydraulic bulldozers were more dangerous than the cable machines they replaced. Studies from that period showed hydraulic bulldozers operating on American construction sites had a fatality rate of 1.8 deaths per 100,000 operating hours, compared to 1.2 for cable systems. That is 50% higher. The early hydraulic systems used fittings and rubber hoses that were not rated for the pressures they experienced on heavy earth-moving equipment. Hydraulic lines burst without warning on job sites, spraying fluid at temperatures exceeding 300 degrees Fahrenheit. The fluid itself was toxic. And unlike a cable failure, which was loud and visible on a noisy construction site, a hydraulic failure could be silent. A pinhole leak in a high-pressure line could inject hydraulic fluid through skin and into the bloodstream. This was almost always fatal, if not treated within hours. And in the 1950s, most remote construction sites were hours from the nearest hospital. It was not until around 1960 that hydraulic systems became reliably safer than cables. Better hoses, better fittings, better pressure relief valves. The technology caught up to the promise. But for a full decade, the safer alternative was actually killing more operators than the system it was supposed to replace. This raises a question that rarely gets asked. If the industry knew hydraulics were not yet safer, why did the transition happen at all? The answer was economics, not safety. Hydraulic systems were faster, and they allowed more precise blade control. An experienced hydraulic operator could move 15 to 20% more earth per hour than an experienced cable operator. On a highway project moving millions of cubic yards, that productivity gain translated to hundreds of thousands of dollars in savings. Contractors could bid lower on government projects and still profit. The federal government, which was funding the interstate highway system through the Federal Aid Highway Act of 1956, wanted projects completed on schedule and under budget. They were not asking how many operators were dying in the process. Safety was not the driver of the hydraulic transition. Profit was. The cable-era operators knew their machines were trying to kill them, and they developed survival techniques that were never written down in any manual. The most important was something they called the Widowmaker Stance. An experienced cable bulldozer operator never sat on the open steel seat the way a modern operator sits inside a climate-controlled cab. They positioned their left boot on the edge of the metal platform, their right foot forward on the steel floor plate, weight on the balls of both feet. From this position, crouched slightly forward on the exposed deck of the machine, they could launch themselves backward off the bulldozer in roughly half a second. It was not comfortable. It was not ergonomic. But operators who used it had an estimated 30 to 40% better survival rate in catastrophic cable failures compared to operators who sat back in the seat. The difference was simple physics. A man sitting back in a steel seat needed over a full second to stand, turn, and jump. A man already on the balls of his feet, already leaning slightly away from the danger zone, could clear the cab before a whipping cable completed its arc. This technique was passed from experienced operators to new ones on the job. It was never documented in any Caterpillar manual, never taught in any training program. When the cable era ended, the knowledge went with the men who had needed it to survive. If you have made it this far, you are clearly interested in this kind of content. Hit subscribe so you do not miss the next one. There was another survival skill that has been almost completely forgotten. Cable singing. A steel cable under tension vibrates at a specific frequency, just like a guitar string. The pitch depends on the cable's length, tension, and condition. A healthy cable under proper load produced a steady, consistent hum. Experienced operators learned to listen for changes in that hum. A drop in pitch could mean the cable was stretching. A change in the harmonic pattern could indicate broken internal strands. A sudden shift from a steady hum to an irregular buzzing often meant failure was minutes or hours away. The problem was that the diesel engines on these machines produced sustained noise levels well above 100 decibels. Over months and years, that noise destroyed the operator's hearing, and the operators who lost their hearing lost the ability to hear the cables warning them. Records from the period, as they exist, suggest that operators with significant hearing loss had disproportionately higher fatality rates from cable failures. They could not hear the one warning system the machine actually provided. This created a vicious cycle. The machine deafened its operator. The deafened operator could no longer detect cable deterioration by sound, and so the deafened operator was more likely to be killed by the cable failure he could not hear coming. Now here is perhaps the most disturbing fact in this entire story. In 1947, 3 years before the decade we have been discussing, Caterpillar produced an internal engineering memo. The memo was declassified and became public in the 1990s. It calculated what the company called an acceptable casualty rate for cable-operated bulldozers. The math was straightforward. With approximately 15,000 cable bulldozers operating in the United States and an observed failure rate that produced roughly 1 death for every 50,000 operating hours, Caterpillar's engineers estimated approximately 600 operator deaths per year attributable to their machines. The memo then evaluated potential safety improvements. Cable guards that would contain a whipping cable within the operator station, enclosed cabs that would protect operators from weather, noise, and debris, improved cable metallurgy that would reduce the brittle fracture problem in cold weather. Each improvement had a cost per unit, a projected reduction in fatalities, and a market impact assessment. The memo's recommendation was to implement none of them. The stated reasoning was that the market, meaning the contractors who purchased the machines, had accepted current rates. Implementing safety improvements would increase the per-unit cost of a D7 by an estimated 8 to 12%. That price increase, the memo argued, would push buyers toward competitors like Allis-Chalmers and International Harvester, companies that were not adding those costs. The memo concluded that the business risk of losing market share outweighed the liability risk of continued operator deaths. 600 deaths a year calculated, documented, and accepted as a cost of doing business. The memo was buried for 45 years, and there was no one to push back. Unlike coal miners, who had been organizing since the late 1800s, bulldozer operators had virtually no union representation. The United Mine Workers fought for ventilation standards, safety inspections, and compensation for black lung disease. Those fights made headlines. They generated public pressure. They forced regulatory action. Bulldozer operators had none of that. They were typically independent contractors or employees of small construction firms. They had no collective bargaining power, no lobbyists, and no public awareness campaigns working on their behalf. The result shows up in life expectancy data. The average bulldozer operator in the 1950s and the 1960s had a life expectancy of 58 years. Coal miners, who everyone thinks of as having the most dangerous job in America, averaged 62. The U.S. male average was 66. Bulldozer operators died younger than coal miners. Almost nobody knows this because there was no one whose job it was to tell the public. The regulatory response, when it finally came, took until 1970. That year, Congress created OSHA, the Occupational Safety and Health Administration. In 1971, OSHA mandated rollover protective structures on all new heavy equipment. In 1972, seatbelts became required. Over the following decade, enclosed cabs, backup alarms, and dozens of other safety features became standard. The fatality rate dropped, not overnight, but steadily, from 75 per 100,000 in the 1950s to around 30 in the 1980s to 9.6 today. If you are finding this kind of history interesting, subscribe now. I have a full series planned on heavy equipment disasters and the safety changes they forced. But the drop in fatalities came with a trade-off that is worth acknowledging. A modern Caterpillar or Komatsu bulldozer operator sits in an enclosed, climate-controlled cab with electronic joystick controls, GPS grade guidance, automatic blade control, 360-degree cameras, and proximity sensors. The air-conditioned cab has tinted windows, a suspension seat, and a stereo system. The machine protects the operator from almost every failure mode that killed the cable-era men. The modern operator is safer. That is an unqualified good. But the modern operator also does not need to understand how the machine works at the mechanical level. They do not need to listen to the cables. They do not need to feel the clutches engage through the lever. They do not need to position their feet for a half-second escape. The survival knowledge of the cable era, the Widowmaker Stance, the ability to hear a cable approaching failure, the instinct for which Pulley was about to seize, all of that is gone. That knowledge was never written down. It existed only in the hands and ears and instincts of men who are now in their 80s and 90s, if they are alive at all. In 30 years, there will be no one left alive who operated a cable bulldozer professionally. The last generation of men who sat on those open steel seats, who pulled 40-pound levers with bare hands, who listened for the hum of a cable about to fail over the roar of a diesel engine, will be gone. And with them, an entire body of knowledge about how humans and machines survived together in an era before anyone in authority thought survival was worth engineering for. The 1950s cable-operated bulldozer did not have a safety committee. It did not have an OSHA poster on the wall of a job site trailer. It did not have a training manual that covered what to do when a steel cable under 12,000 pounds of tension was about to fail. It had the operator, alone on an open platform, hands on steel levers, boots on the edge. And for 600 men a year, that was not enough. Between 1945 and 1970, cable-operated bulldozers moved billions of cubic yards of American earth and helped build the infrastructure that modern America runs on. The concrete highways you drive on every day, the massive dams that generate your electricity, the deep foundations under the buildings where you work. Those yellow machines were built to move dirt. They were not built to keep their operators alive. And for 25 years, nobody with the power to change that thought. It was worth the cost. That calculation, 600 acceptable deaths per year, is the number that defined an era. And the men who sat in those open cabs, feet positioned on the edge of the platform, listening for a change in the hum of the cable, they are the ones who paid for it. If you want to see how another piece of heavy equipment turned into a disaster, the video on screen right now covers one of the worst crane collapses in construction history. Click it now.